Good morning, everyone. It is a pleasure for me to introduce Robert Heiss, the CEO of Atom Computing from the United States. Robert will talk about scaling quantum computing with neural atoms. Rob, as CEO and president of Atom Computing, has a growing startup company building quantum computers out of optical trapped neutral atoms. Robert has over 20 years of technology leadership, pursuing the limits of computing performance and accelerating innovation. Rob was previously Chief Strategy Officer for Lenovo's Infrastructure Solutions Group. And prior to that, he was Vice President and General Manager for Intel's Xeon processor roadmaps. A pleasure to have you here, Rob, and we are eager to hear about you and your computers.
Great. Thank you, Martin, for the nice introduction. And hello, everyone. Good morning. I will share my screen and introduce myself and Atom Computer to you. Okay. So, yeah, I'm Rob Heiss. I've been the CEO of Atom Computing for the past year, and I joined the board back in 2020. It was founded by Ben Bloom and Jonathan King, who have PhDs in physics and chemistry, respectively. They founded the company back in 2018, and I'll tell you a little bit about what we're doing and how it's different than some of our competitors. So this is our team. We were founded in Berkeley, California, but we've also expanded now into several other locations. I'm talking to you from Cary, North Carolina. We are building quantum computing hardware platforms, and we're doing it out of optically trapped neutral atoms. As you guys all know in the community here, that quantum computing is really one of these once-in-a-generation paradigm shifts in computing performance. It has the opportunity to really transform computing technology and research in many different industry verticals and many applications within those verticals. Some of the early adopter kind of industries that we see a lot of interest in are transportation and logistics, financial services, pharma, chemistry, material science, defense, and energy. We as a hardware platform provider have a mission that's crystal clear. It's building large scale computers as measured by the number of qubits with error correction so we get the right answers. And it turns out that's actually a really hard problem to go solve. And so that's what our team is working on. You're probably most familiar with superconducting and trapped ion-based systems. These were the early kind of initial modalities for quantum computing that have been around for over a decade now. Obviously, IBM, Google, and Rigetti are kind of well known for superconductors, and IonQ and Continuum for ion traps. These are technologies, like I said, that have been around for quite a while, and they've been the platforms on which pretty much the entire industry has kind of bootstrapped ourselves and figuring out how to build quality qubits, get the fidelities up, learn how to benchmark these, build the gate sets, the software, the developer kits, and all that. And so I think we collectively owe a big tribute to the companies and the people that pioneered on these platforms. It turns out that these two technologies in particular are reaching scaling limits, or it's very difficult to scale them to very large numbers, thousands, tens of thousands, even millions of qubits into the future. And so that's why Atom Computing and other companies in the industry have really started to pop up and look for I'll call it a better way or a more scalable way. So I'm borrowing this quantum computing market map from the Quantum Insider Group. And this just shows you not all the companies, of course, that are involved in quantum computing, but a large number of the more well-known ones. And we are a hardware provider. So we're in the QPU, or the quantum processing unit section. And you can see superconducting and ion trap companies listed there. And we're doing what's referred to as neutral atoms. I'll talk more about how it works in a second, but basically neutral atoms, some of the silicon-based technologies and photonics are kind of the next wave or emerging technologies that have the promise of being more scalable to up to millions of qubits. And so that's what we're looking for. And there's other companies, in our modality, as well as others that are also trying to achieve a similar scale with quantum computing. And so we're all collectively looking for this massive scale large numbers of qubits. And it turns out that we at Atom Computing are finding it in the tiniest of places. We're finding it inside of individual neutral atoms. So neutral atoms are alkaline earth elements or alkaline earth-like elements in the second column of the periodic table. It means they have a closed shell, an equal number of protons and electrons, which means that they are very stable and don't interact with the environment around them without some kind of stimulus to excite them. So we take these atoms in a vacuum chamber and we trap them with an array of what's called optical tweezers. And so we basically shine lasers through a microscope objective into the vacuum chamber, and the atoms that are floating around in a gaseous form get kind of stuck in the focal point of light. We can then control where those atoms kind of sit in three-dimensional space by steering the laser beams, and we can control their quantum states, the nuclear spin or the what's called a Rydberg state of the electron cloud with laser pulses in different colors of light, and very precise control of amplitude, frequency, phase in order to get those atoms to do what we want them to do. We encode the qubits in the nuclear spin. And these atoms or these qubits show very long coherence times and other favorable properties that we believe make it a very good platform in which to build quantum computers of massive scale. To kind of show you what it looks like, on the far left here on this slide, we have an image of inside of our system. And what you're seeing is this is kind of like a slowed down stop motion video of individual atoms that are trapped in free space, and we're able to rearrange them into a fully ordered array. And we need that fully ordered array in order to drive computation and entanglement between adjacent atoms. And so we're able to capture these atoms with these individual laser beams and move them around and then write their quantum state. Today, we have a 100 qubit prototype system that I'll show you in a few minutes. That system is a 10 by 10 array of lasers. These spots of light or these qubits are placed 4 microns apart. So that means that system is 36 microns on a side. So very, very tiny. In order to scale up the system from hundreds to thousands and eventually millions of qubits, we'll just create more spots of light. So to go from 100 qubits to 10,000 qubits, we simply need to do 10x more lasers on each side. And that's still in a very tiny space, given the 4 micron pitch between the atoms. And to get to 1 million qubits, we just take that and create 100 layers of it in a 3-dimensional array, and we get 1 million qubits at 100 by 100 by 100. And again, at 4 microns apart, that fits in less than 1/10 of a cubic millimeter in space. So very tiny and very scalable because it's wireless. We don't need to put wires or cables up to each qubit, unlike superconductors, for example. And so it's just much more straightforward and to scale, and it's all around creating technology to control those individual points of light. So here's a picture of our current prototype system. We call it Phoenix, 100 qubits. This was completed last year, and right now we're working on getting up our gate fidelities and tuning up the performance, getting the software stack complete, and then working with partners for beta testing on this system kind of privately. You can see on the far right, there's a metal cylinder, a steel cylinder. That's the vacuum pump. The vacuum chamber where the qubits sit is sort of behind it. You can't really see it in this picture, but I'll show it to you on the next photo. In the middle of the image there, you see a lot of kind of devices and some cables and things like this. These are optical acoustical devices and electronics to control them. In this prototype system, they were all hand placed for maximum flexibility and experimentation. In future systems, those will all be kind of CAD designed and machined and much more kind of precisely oriented. So we'll give up some flexibility, but we'll gain quite a bit of quality and reliability as we kind of learn from the experiment on the Phoenix platform. And then next to the system, kind of in the back that you can't see very well, is a rack of servers and the control system that controls the laser pulses. And those servers are just running a standard software stack for the compiler, the scheduler, the APIs, how people interact with the system through a standard software APIs. This is what we call the heart of Phoenix, lovingly. So if you kind of got into that system and you look behind that vacuum pump that I showed you on the previous slide, you'd find the actual vacuum chamber. and it's about the size of my palm. It would fit in my palm, and that's where the qubits sit. And it's basically like two glass windows on the top and the bottom with a little bit of space between them for where the vacuum is and the qubits sit. And we have microscope objectives kind of up against those glass walls, and those are where the lasers are focused through through the windows into the glass into the vacuum chamber, as well as a microscope objective with a camera that reads out the results of the circuits that we run. Just recently, we had a technical paper published in Nature. You can see the URL in the bottom there that demonstrated world record coherence times on our qubits. So this is the first time that coherence times in the tens of seconds on all qubits had ever been demonstrated. And we showed 40 seconds on all qubits. Superconductors are getting like microseconds of coherence time up to milliseconds. So it's these are orders of magnitude longer than other modalities. And the reason that coherence time is important is that's how long the qubit state or information is held inside the qubits. And so you can basically, the longer the coherence time, the more stable the platform to run, large circuits with error correction. You don't have to worry about that information disappearing in the time that it takes to compute the circuits and perform the error correction, which is a feedback loop between the quantum hardware system and a classical software system that is detecting and correcting for errors as you're executing through a circuit. So we're very proud of the long coherence time. It's a great platform. It shows that neutral atoms has a lot of promise to be a scalable platform. And while we're kind of proud of our number of qubits and how fast we're able to deliver them and our world record coherence time, those are just two of many performance attributes that go into the overall performance and quality of a system. And so I'm kind of showing you an example of what other attributes, and this is not exhaustive, mutually exhaustive, but it's a good representation of different kinds of system attributes that add up to overall system behavior and performance. And so you have number of qubits or the size of the system, coherence as, again, how long the quantum information stays in the qubits. You've also got connectivity. Connectivity is important. Some systems are modular, some are monolithic. Ours is monolithic. Some systems are all-to-all connectivity within a module. Some are a subset as far as how you can get entanglement. But that leads to different topologies and different levels of parallelization and computation that you can run based on the connectivity. You've also got fidelity, which is just the inverse of error rate. So you have a 1 error out of every 1,000, you'd have a 99.9% error fidelity. And so obviously the lower the error rate, the better the fidelity. The better the fidelity, the deeper the circuits you can run with fewer errors, et cetera. So that's very important for performance as well. And then there's other attributes. IBM I introduced something called CLOPS recently. That stands for circuit layer operations per second. It's kind of like an aggregate throughput indicator that shows, in aggregate, how many operations could you perform given sort of multiple attributes of a system. And I guess I'm kind of showing a system A and system B here. These are not real examples. These are sort of made up examples that kind of represent kind of where systems kind of are today. But the point is that different systems and different architectures will have different performance attributes, and those will all ultimately add up to different, overall system performance for the platforms. So our job, as a quantum computing hardware platform company, is to try to expand on all of these kind of simultaneously and push the boundaries of all of them over time, so that we get better and better performance and greater system capabilities for larger and larger problems. And that, at the end of the day, is our sole focus at Atom Computing, is just driving scalable quantum computing with high performance. So we recently announced that we raised a Series B in funding. We raised $60 million, and we're using those funds to develop our next generation quantum computers. That's in process now. Our plan is to launch them as a public cloud service with one of the major cloud service providers. And we are right now building software and service provider partnerships that can help us and the partners advance on our journeys and start to build customer relationships and ultimately deliver a great customer or user experience with those partners together. And so that's where we are in our journey and what's next for us. And I want to thank you for your interest, and I will open it up for questions for the remaining time.
So great presentation, Rob. Thank you very much for all the explanation, and it's very interesting what you are doing, and congratulations for the series that you got recently.
Thank you.
So I would like to ask you, as you are in the hardware layer, how we can work from the software application layer. You are saying that you will be publishing the access to the computer through cloud providers. So what would be the basic software applications that I could use to work in the software layer?
Yeah, great question. So we are kind of play our role at the hardware provider layer, and so we'll support kind of at the popular software developer kits. So currently we support Qiskit and OpenChasm, but we'll also support Circ and others over time as we get that software completed, or those kind of interface layers completed. And so that's how we kind of nominally intend to interact with users or developers, is through those popular developer kits, so they could compile to our platform or somebody else's platform, make that code portable and easy for the developer. We're also partnering with quantum application providers. Many of these are also startups themselves that have expertise in quantum software development or physics, and they're trying to figure out how to apply quantum computing to various industry vertical applications or problems, like I mentioned before, like transportation logistics, mapping problems, portfolio optimization, drug discovery, these kinds of things. So we're partnering with a number of these companies. We've already signed MOUs with, I believe, 16 kind of application providers. And so we'll work with them privately to do beta testing on our system prior to launch, and make sure that they're kind of ready to go in steering their customers onto our platform as we launch in the coming months. And so those are the two primary ways that we would interact with customers, whether they want to develop their own on sort of the popular SDKs or work with an application provider that we could help matchmake if they need.
Very good, very good. So if how the different stakeholders can start engaging today with atom computing? Either I'm a researcher, I'm a startup in quantum, a technology company focused on quantum, or an end customer. Based on your timelines, how each one can map and start engaging with you?
Yeah, so if you're a researcher, there's probably a couple ways you could engage. One way is you may want to come work for us. So we're hiring across engineering, physics, software, business roles, a number of different roles. So there's always that opportunity. You can check that out on our website. But we also do collaborations with universities and government labs on advanced technology development. We obviously have a roadmap like any company would, and we require advances in technology for optics or controls or things like that. And so we've got a number of research projects that we're either sponsoring at universities, or maybe the government entities are sponsoring jointly with us and universities and government labs. So we're very interested in engaging on advanced technology development. If it's more on the software and applications side, then it would be probably best to engage with some of our partners who are working on the applications, and we can help you. Anyone who wants to get engaged with us can reach out to me. You can find out how to contact us on our website, and we can engage in a proof of concept project or something like that. Over time as the systems are available to end users.
Right. I have a question from Alberto in Venezuela. He is asking if inside the company scope there is something around the quantum teleportation.
Oh, that's a good idea. We're not working on that today. There are a number of companies that are working on quantum, networking and communications, but no, we're really focused on quantum computing, and specifically gate-based quantum computing, using the universal gate set that IBM and Google and others are using as well.
Very good. Christian is asking from Colombia about the coherence time, if it could be increased even more, and if so, how you think it could be done?
Yeah, I think I don't think I can't answer that question, so I apologize, but I won't try to dive into something technical that's beyond my experience.
Great. My colleague Araceli, now from Barcelona in Spain, is asking about how or what do you think about those eager users that are demanding things about quantum computing for results in the short term, and how important it is to be realistic in the quantum computing roadmaps?
Yeah, critical to be realistic. There's a lot of hype in quantum. I think that's something that really kind of irritates a lot of us in the industry and in research. Hype doesn't really help anyone. Real science and engineering is what it's going to take to get this done. And to be perfectly frank, like the reason we're not launching, Phoenix as a commercial system is there's not a lot that you can do with 100 qubits. The systems that are out there today are all dozens to maybe 100 or 200 qubits. They're great as a research platform for people that are trying to figure out, like how do you interact with the system? How do you program it? What kind of performance can you get out of it and results? So I think those are great. We use other people's platforms for that, even internally, to learn, but as well as our own. But I don't think we're going to see a lot of commercial value until we get to probably a few thousand qubits, and honestly, even more than that. But we do have identified some early use cases with our partners that we think with a few thousand qubits that there probably is some commercial value. Maybe just speeding up scanning solution space, for that you can take a large set of potential answers and narrow it down to a more focused set of potential answers, and then maybe use more classical HPC or something to do further simulation on that. So I think that there will be some things that we can do in the next few years, but until then, it's really supporting the researchers, the both corporate researchers as well as academic and government researchers on our platforms. We will be able to collect some revenue on our system on giving people time on it for that purpose, but it's not like broad scale commercial value, probably for the next 3 to 5 years at a minimum would be my expectation.
Very good. More questions, technical questions about materials. So Diego is asking from Tampa if you have considered using biomaterials to increase coherence time.
So ask that one more time just to make sure I understand the question, if you don't mind.
No, the question is if you have considered biomaterials in order to increase the coherence time.
Not inside of our system. Using our system to do research in that area, I think, is an area inside scope. So yeah, I think that's more of an application maybe of our system than a material inside of our system, if that's the question.
Good. Guillermo from Argentina is asking us about quantum machine learning. You are in the hardware layer, but how do you see your platform collaborating in this quantum machine learning?
Yeah, I mean, at the end of the day, machine learning, especially like neural network learning, is it's trying to help machines infer something. What word was said, seeing, computer vision, autonomous driving, things like this, right? And so it's all around training a model that helps inference be more accurate and faster. And this is actually a good application for quantum computing because quantum computing can kind of simultaneously scan a very large probabilistic solution space and help figure out what the most probable answer is. And at the end of the day, that kind of is inference, right? So I think quantum computing will fit right into the kind of neural network and machine learning workflow as these systems, start to work and become accurate and all that. So there's a little bit more work to be done on the hardware side to make it useful, but I think that's a very natural use case. And I don't think it won't replace like classical compute neural networks using CPUs and GPUs. I think it'll just be part of the workflow where there'll be some stage in the network that's offloaded to a quantum processor for some computation, and then it'll go back in. And so this will probably be used in model training. And I don't know if it probably won't go into inference processors anytime in the near future, like in the next decade. But certainly for training models, I think it'll be high
Well,
value.
very well. More questions for you. So in this case, Kevin from Idaho, the Idaho National Laboratory, is asking if you use any epitaxial systems on your research.
Say the word again.
Epitaxial.
I don't even know what the word means. So if you stumped me again, I apologize.
Epitaxial systems. Okay, probably.
I don't know what epitaxial is. So, yeah, thanks for sharing it. I don't know. It's possible. I apologize. It's beyond my expertise.
Okay. So, I will invite Kevin to post a question to Rob on that.
Okay. Yeah, by the way, I'll give out my email address. Take a little risk here. Rob, R-O-B, @atom-computing.com. So if anyone wants to ask a question afterwards, I'm happy to find the answer for you from one of our scientists or engineers.
Okay, very good, very good. Great presentation and very interesting questions from the audience. So Rob, thank you very much. We are very pleased to have you here. And well, all the best with this. And we expect this quantum future soon.
Wonderful. Thank you, Martin. Thank you, everyone, for your time and interest. I appreciate it.
Great, great. Thank you very much.
Bye.